Hello everyone, my name is Subash and today we are making a big shift, moving from descriptive analytics, which is about understanding what had already happened, to predictive analytics, specifically the art of science of forecasting. By the end of the session, you will not only understand what forecasting is and why it matters, but you will also have a solid toolkit of models you can apply in real marketing situations, from predicting seasonal sales to modeling product adoption curves. Let's get started. Here is a quick roadmap of everything we will cover today. We have six main sections. First, we will define forecasting and ground ourselves in why it is such a critical capability in marketing. Then, we will dig into mathematical foundation, the linear equation, before moving on how we measure whether a model is actually working well. From there, we will look at what happens when the data does not follow a straight line, that is, our nonlinear model sections. We will then tackle seasonality, which trips a lot of forecasters, and finish with S-curves, which are especially powerful for understanding product adoption. We will close with a summary slide and a decision guide you can use when choosing a model in your own projects. So, what is forecasting exactly? At its core, forecasting is the process of using patterns in historical data to make predictions about the future. We are essentially building a model of reality, then using that model to look ahead. In marketing specifically, this shows up in four major ways. Sales forecasting helps us to manage inventory and supply chains. You don't want to run out of product in December or be stuck with too much in February. Demand forecasting tells us how to adjust our promotional strategies based on anticipated customer needs. Budget forecasting lets us allocate marketing spending intelligently rather than just repeating last year's numbers. And trend forecasting helps us get ahead where customers are going, which is especially valuable for product development teams. The key thing to understand is that forecasting is not guesswork. It is disciplined, model-driven prediction based on data, and the quality of your forecast is directly tied to the quality of your model. Now, before we go deep on any single model, let's do a quick survey of the landscape. There are five main types of model we use in forecasting, and each one is suited to different kind of relationship in the data. Linear models assume a straight line relationship between variables. They are the simplest and most widely used, and you will see they are actually the foundation for everything else. Let's say we are studying how advertising impressions, the number of times someone sees an ad, affects brand recall, which is whether they can remember the brand without any prompts. The slope, M, tells us how much recall changes for each additional impression. In our data, the value is 0.82. So every time someone sees the ad one more time, we expect brand recall to go up by 0.82 points. The intercept, B, is our starting point. The expected recall when impressions are 0. Here it is 0.86. That tells us there is some baseline brand awareness even without advertising. The independent variable X is what we control or observe. In this case, impressions. The dependent variable Y is what we are trying to predict, recall. This simple equation is remarkably powerful. It lets us say if we run 10 more impressions, here is what we expect recall to look like. That is a forecast. Okay, we have built a model, but how do we know if it's actually good? There is That is why fit statistics come in. Every model has error, the gap between what it predicts and what actually happened. Our job is to understand and minimize that error. But, and this important, we never want to obsess over a perfect fit. A model that fits the past perfectly often fails to predict the future well. The four key statistics we use in this course are R-squared, MSE, p-value, and AIC/BIC. R-squared tells us how much of the variation in our outcome is explained by our model. The value of 1 would be perfect, But in marketing, anything above zero point 0.7 is generally considered strong. MSE, mean squared error, measures the average size of our predictions error. Lower is chance. We typically look for p-values below 0.05. Finally, AIC and BIC are especially useful when comparing multiple models. They balance how well the model fits against how complex it is. A simpler model that fits nearly as well as a complex one is generally preferred. Now that you know how to measure fit, let's talk about the traps that catch even experienced analysts. Overfitting is the big one. It happens when your model is so tuned to your training data that it captures noise instead of real patterns. It looks great on paper but falls apart when you apply it to new data. Ignoring model assumptions is another common mistake. Every statistical model comes with conditions that need to be true for the results to be valid. Things like linearity, independence, and normally distributed errors. Skipping the assumptions checks is like building on an unexamined foundation. Confusing correlations with causations is perhaps the most famous error in data science. Just because two variables move together does not mean one is causing the other. Always ask yourself, is there a logical mechanism here, or am I just seeing a coincidence in the data? Relying on stale historical data is a real problem in marketing, where consumer behavior can shift quickly. A model built on pre-pandemic data may be useless post-pandemic. Poor data preparation and ignoring external factors round out our list. Garbage in, garbage out, and if your model does not account for economic conditions, competitive dynamics, or major world events, it will have blind spots. So far, we have been working with straight lines, but the real world is rarely that simple. Consumer behavior curves saturates and accelerates in ways a linear model cannot capture. That is where nonlinear models come in. Power models follow the form y equals a times x to the power of b. They are useful when growth is proportional to exposure. For example, how quickly a new product gains market share as advertising spend increases. Logarithmic models capture diminishing returns. The formula is y equals a plus b times the log of x. Think of advertising fatigue. The first few impressions of an ad are powerful, but by the hundredth, you have tuned it out. That curve is logarithmic. Exponential models describe rapid accelerating growth. Y equals 8 times e to the bx. Viral social media campaigns often follow this pattern, at least in the early stages. Polynomial models are flexible. They can fit curves with multiple peaks and valleys, but be careful. They can overfit easily and outside the range of your data. They can produce widely unrealistic predictions. Use them when you genuinely have cyclical, multidirectional data, and always check the behavior at the extremes. Let me ask you something. If you were a retailer trying to forecast greeting card sales, would you trust a linear model that just draws a straight line through your data? Probably not. And that is the core problem seasonality solves. Seasonality refers to predictable, recurring fluctuations in data. Think holiday spikes, summer slowdowns, back to school rushes. These patterns are regular and foreseeable, but a straight line completely misses them. We handle this with two main approaches, the additive model and multiplicative model. In the additive model, we take our linear forecast and add a seasonal index, a fixed amount that adjusts the prediction up or down based on where we are in the cycle. This works when seasonal swing stays about the same every year. Our Hallmark cards example is a good illustration. The December spike is predictable and consistent. The multiplicative model uses multiplication instead of addition. This is the right choice when seasonal swings grow proportionally as the overall trend grows. A fast-growing e-commerce business, for example, might have holiday sales that are not just big in absolute terms each year, but proportionally bigger, a larger fraction of annual revenue. The key question is to ask yourself, does the seasonal pattern look about the same on a raw chart? Same height every year? Additive, does it look like it's growing along with the trend? Multiplicative. Now let's talk about one of the most elegant models in marketing analytics, the S-curve. The S-curve describes a very common and very important phenomenon, how new products, technologies, and ideas spread through a market. The pattern is always the same: slow initial adoption as early adopters experiment, then a rapid acceleration as the majority joins in, and finally a plateau as the market saturates and there are fewer and fewer new customers to win. If you have ever seen the classic technology adoption curve, innovators, early adopters, early majority, late majority, laggards, that is in an S-curve in action. In this course, we work with two specific S-curves model, Pearl and Gompertz. The Pearl model, based on the logistic function, produces a symmetric S-shape. It works well when the forces driving adoption, word of mouth, network effects, operate symmetrically through the adoption process. The Gompertz model is asymmetric. It front-loads the slowdown, reflecting situations where products face significant initial skepticism or require a long learning curve before taking off, but then eventually reach their potential. In Excel, we fit these models using Solver, which finds the parameter values that minimize the error between our model and the actual data. We practice this in the lab. Alright, we have covered a lot of ground. The natural question now is how I know which model is to use for my data. This decision table is your guide. The first thing to do is look at your data visually in a scatter plot. What does the pattern look like? If the growth looks steady and consistent, start with simple or multiple linear regression. Watch your R-squared and p-values. If growth looks like it's accelerating rapidly, especially in a digital or viral context, try an exponential model and evaluate it using MSE on a holdout dataset. If you are modeling advertising or marketing spend where you expect returns to diminish over time, the logarithmic model is your friend. Compare its AIC or BIC to a linear baseline. If your data clearly rises and falls with the calendar seasonality, use an additive or multiplicative seasonal models. And always do the visual residual check. Pearl or Gompertz are designed exactly for you. Focus on how accurately the model predicts the saturation level. And for complex multidirectional data, polynomial models can fit, but use them with caution and always check for oscillation outside your matter. But a perfect fit is a warning sign, not a victory. Always ask whether your model will generalize to new data. Fourth, before you trust any model's output, check its assumptions. Linearity, normality, no overfitting. These checks are not optional. They are what separates a reliable forecast from a number that looks good but misleads. And fifth, match the model to the data pattern. Seasonal data needs seasonal models. Adoption curves needs S-curves. The goal is always to pick the tool that reflects the actual behavior you're trying to predict. Thank you. I'm happy to take any questions, and remember, we put all of this into practice in the Excel labs.